Hello, thank you for joining me. My name is Michael Kubacki. I'm a software engineer at Microsoft, and today I'll be covering PRM, Platform Runtime Mechanism, what it is, what we are using it for, and what we're going to do with it going forward. As part of this platform runtime mechanism effort, there were a large number of people involved across both Intel and Microsoft. This was truly a collaborative effort between the two companies. I'm listing some of the major contributors here. A lot of these people have worked on the firmware and the operating system side of the technology and have contributed many ideas and code to making this possible. As part of the agenda, we'll cover system management mode, what it is for those unfamiliar with it, why we might want to have it go on a diet, what PRM is and how we're planning to use it, how does it help mitigate some of the issues that we'll discuss with SMM. And finally, we'll cover the SMM to PRM transition. So this will be how we go from SMM to PRM, because we can't just do it in one shot. This is SMM goes on a diet, not that we're killing SMM. So we'll talk about how we go from SMM to PRM. And then we'll cover the open source firmware side of this, so how you can access the code, and what type of documentation is available to help you get started if you're interested in learning more. And then finally, the current status. So system management mode is a special operating mode in x86 architecture. It's used to monitor and manage various system resources. Some examples of SMM are given here. Quite often it's used for power management code. So this would be things like SX callbacks. So you can have like a S3 and S4 and S5 callback inside SMM. And so whenever the operating system goes into one of those modes, you can have code run that's at the platform firmware level. And so that can be useful if you're trying to deploy code to a lot of systems without having to necessarily write drivers to handle what you want to happen on those power state transitions. OEM code also operates in an isolated execution environment. And so this can be useful if you need a ubiquitous isolated environment on something like the x86 architecture, where you can do authentication and process confidential sensitive data. Sometimes SMM is used for use cases like that. And then over on the right side, firmware handling of system events. And so SMM code typically is very platform and silicon specific. So one of the unifying features of SMM is that it might be used to handle a bunch of like hardware or thermal events that are very specific to the platform. So looking at the right side, we have the firmware handling of system events. This covers things like compatibility, hardware, and thermal. So this might be able to be used to handle like hardware events that happen, such as a memory error or some other type of error in the system, or a thermal event. And so, again, this goes back to SMM being used for a lot of platform and silicon-specific functionality. And it's a way to ship that without having to deploy OS drivers necessarily. So you can ensure that you're able to execute that code on all the systems that might be used, regardless of the operating system. SMM is entered via a system management interrupt called an SMI. There are hardware SMIs and software SMIs. Software SMIs allow software to synchronously trigger an SMI by writing to an I/O port, like the B2 I/O port on the Intel architecture. And hardware SMIs are asynchronous, so they can be generated by something like the PCH in response to some device that might need to trigger an SMI. So the drawbacks of SMM, it's difficult to debug. And so if you're an operating system engineer or you're someone working in general system software, you don't really have visibility into SMM on the system. And so it can kind of take over on your system. You can enter into an SMI and you might not have an interrupt service whenever you expected it to, or you might not have, your code execute necessarily in the fashion that you expected. So you might see some performance glitches or things like that. So whenever that happens, it can impact your code depending on what your code is doing, and it's very difficult to debug that because it's running in a separate execution mode outside the normal operating system context. It's difficult to manage and secure. So SMI handlers do run with their own page tables, and they have a higher privilege than ring 0, sometimes called ring -2. It's non-maskable and uninterruptible. And so what this means is you don't really have a lot of control of SMM on your system. It's going to happen when it needs to happen. and your code might be impacted. And so in all, there's a largely a negative performance impact that can occur on a system due to SMM. So in order for the system to actually go into SMM, all of the cores have to go in through what's called a rendezvous. This is where the cores all wait for every other core to enter into SMM. And depending on the nature of the system, such as your number of cores, sockets, and what the system state is, such as if it's in a C6 power state, it can take a long time to go into SMM. And so the amount of time that you spend in SMM, we generally call SMM latency. To give you an idea, on like a typical 4-socket server class system, SMM latency can be between 300 microseconds and 1 millisecond. And so that can have a significant impact on system software depending on what you're planning to do. Also, for things like real-time operating systems, you might need to service an interrupt within 10 microseconds or so. And so we have found that just going into an SMI and coming back out on an Intel Atom system can take around 20 to 40 microseconds. And so if you are trying to service your interrupt within 10 microseconds, that alone can prevent that from happening. And so in general, SMIs can also occur at inopportune times, such as during a long flow instruction. So examples here are write back and validate and micro-patch code load. And so if you're executing one of those instructions, the SMI actually enters on an instruction boundary. And so you could have inconsistent amount of time it takes to enter into SMM, depending on what the system is doing when the SMI occurs. And that can, of course, lead to unpredictable performance jitters across the system. One other trait of SMM is that it ships as part of the platform firmware. So this is the SMM environment actually gets set up during the firmware boot flow. And SMM drivers, after SMM is initialized inside an area of memory called SMRAM, are loaded into SMRAM through the firmware dispatch. And so SMM code requires a system reset in order to update, because you're updating the SMM code on the system flash. There are cases where you would like to move away from that model if possible, because this code is executing at OS runtime. It would be nice to have a mechanism to be able to update code executing at OS runtime without having to reset the system, especially in server environments where resetting the system means disconnecting virtual machine users and a long boot time to get back up. SMI is classified under the following categories. And so we kind of came up with these categories for different types of SMIs to figure out how do we take this large set of SMM code that exists and start to move it to something different. So we talked about some of the things we didn't like with SMM. And so what SMI handlers can we take and move somewhere else? It's kind of the question here. And so in order to do that, we created these 4 categories. In category 1 are SMI handlers that do not require SMM privileges. Example here is address translation. So if you're translating from a system physical address to a DIM address, that's something that can be done without the privilege of SMM. So you don't necessarily need the SMM hardware privilege to be able to do that. That falls under more, very silicon specific, platform specific code where you have knowledge of memory controller in the memory on the system, but it doesn't need the hardware capabilities of SMM. Category 2 is software SMI handlers that do require SMM privileges. Example here, like UEFI authenticated variables and UEFI capsule update. This is taking advantage of that isolated execution environment I spoke of with SMM, where the code executing in SMM is able to do authentication. It's able to do kind of security sensitive algorithms outside the context of the main system software and operating system. And so this is code that does require some of the privileges that SMM provides, because SMRAM is inaccessible to normal system code. And so whenever you do the authentication with SMM code inside SMRAM, you're doing it outside the normal execution path of code and system software in Ring 0. Category 3 code are hardware SMI handlers that do not require SMM privileges. Example here is like memory error correction handling. And so if you have a memory error that might trigger an SMI, you would go into that SMI to be able to resolve the memory error. And this is something where something like RAS, reliability, availability, serviceability, comes into play, where you might be trying to correct errors inside the system inside RAS. This varies, but in general, there are hardware SMI handlers that do not require SMM privileges. And so that's another category that you can look at in terms of moving outside of SMM. And category 4 are hardware SMI handlers that do. Things like CPU hot add and remove. These are things that need hardware privilege that's given to SMM because it's a more constrained and limited execution environment on the system. It's not features or capabilities are available to general Ring 0 software. And so I've kind of said SMM privilege a lot. A basic example of that are hardware resources that can only be accessed from SMM execution context. And so there are a set of registers inside the system that you can only access if you're in SMM. They're not accessible outside SMM. That would be an example. If code is depending on that register, you would need SMM privilege for that code. And so, as it says at the bottom, we can most easily eliminate SMI handlers that do not depend upon SMM privileges. So Platform Runtime Mechanism introduces the capability to move software SMI handlers and a subset of hardware SMI handlers from SMM and into the operating system context. And so by doing that, we are able to execute this code as Ring 0 code, and it's not executing as kind of a black box, distinct from normal system operation. However, it's common for those category 1 SMIs, those are the ones that do not depend on hardware privilege, to occur from a DSM in ACPI. So a DSM is a device-specific method. And so what will happen is a driver will typically in the operating system trigger a DSM because the DSM is going to perform some very platform specific logic that the operating system driver might not have coded in. And so it can trigger a DSM to get that to perform that logic, and then the DSM will do what it needs to do and return back. And the DSM is implemented in ACPI. So a lot of these DSMs today are actually triggering software SMIs underneath to go into SMM. Sometimes the logic is too complicated to put in ASL, ACPI source language. So whenever the DSM gets invoked, it even kind of defers the logic to SMM. So you go from operating system driver to DSM, DSM triggering SMI into SMM. And so this means that PRM should support backward compatibility with this interface. We want these drivers that trigger or that call into DSMs to keep being able to do that even after we move to PRM. However, PRM can leverage this abstraction. And so we can take the DSM and just re-implement it to call a PRM instead of an SMI. So we'll talk about how we do that. And at a high level, then, this means that an SMI handler kind of becomes a PRM handler. So we're moving the functionality that was in the SMI handler into a PRM handler. So now we'll cover some operating system flows on Windows. And we'll talk about how those flows work on a commercial operating system. And a lot of this extends to other operating systems. I'm just covering it on Windows. So this is the PRM high-level loading flow. This kind of shows how we go from PRM modules being on the flash device of the system, going all the way into the operating system. So as we've been discussing, they can be called by OS drivers. Looking over at the far left, you have the kind of flash memory on there in the PI specification, the platform init specs that we use for EDK2 UEFI firmware. We have these constructs called firmware volumes. And this is showing just 2 example firmware volumes that might be on the flash. These things contain drivers that get dispatched throughout the firmware boot. And so the firmware volume Dixie contains Dixie drivers and some SMM drivers. The firmware dispatcher will discover these drivers and dispatch them so that they can get launched and executed, forming your firmware boot flow. At the bottom is the PRM firmware volume. This has 2 PRM modules shown, And then it has some generic PRM infrastructure. Now, you don't have to structure your PRM stuff this way. This is just the way that an example of how to do it is you can put it in a firmware volume, and then you can easily remove and add that firmware volume from your system to remove and add PRM support. And as it shows, the PRM firmware volume includes both modules that contain actual code that will get executed at OS runtime and infrastructure that is used to help load those modules into memory so that the operating system can find them. So over on the right, the first step is the firmware needs to discover the PRM modules in the image. It does that just how it discovers the Dixie and SMM drivers. It then authenticates the PRM modules. It does that just as it does the Dixie and SMM drivers, and it authenticates those as well as they're loaded in the memory. So the authentication is similar there. Number three, it loads the PRM modules into a runtime services code area. Runtime services code is important because that is a memory type that's expected by the operating system for code that will be executed at OS runtime. This is the same memory type that we put the UEFI runtime services in today. And finally, the firmware needs to convey to the operating system the information about the PRM modules that it discovered on the system. It does that through a PRM table, ACPI table. And so the firmware is responsible for constructing that ACPI table with the information that it discovers from the images on flash. Now, that is the main handoff to the operating system. It has two pieces: the runtime services code buffer and the PRMT. That's the code and that's the data about the code. Now, the operating system, in the case of Windows, winload.efi, discovers the PRMT and constructs a list with the cache entries for those PRM modules. So now the operating system has a cache list that it can refer to whenever someone asks to call a PRM handler. Finally, winload.efi fixes up the virtual address pointers to top-level handlers using the EFI memory descriptor list. And finally, winload.efi, which is the OS loader, passes the information to the kernel via the loader block. And so the kernel actually gets the information via this structure called the loader block. And so what all of this is doing is basically putting the code into a memory area that can be executed at OS runtime, passing information about the code through the ACPI table picked up by the OS loader, and in turn moved to the operating system kernel. So how do we invoke PRM? So now that the operating system has information about the PRM modules inside a system, it needs to be able to invoke those PRM functionality in those modules. The code inside a PRM module, you can think of the module just being like a PE32 image that has a bunch of functions inside. Those functions can be executed by the operating system. They are called PRM handlers. So there's two ways to call PRM handlers. As we discussed, there is the ACPI way, which is through the DSM, for example. So the OS driver would call its DSM. The DSM would call a PRM handler. It does that through a new op region type that we are introducing called the PRM op region. It's called platform RT mechanism type for the op region type. And so whenever the DSM gets control, it would form a data buffer. It would fill in some information about the PRM handler it wants to call into the data buffer. And PRM handlers are identified by GUIDs. So it would put the GUID for that handler into the data buffer, and maybe some information like that it needs to give to the handler about information, that it might read a register and pass that data to the handler through what's called the parameter buffer. And then it gives that information to what's called the PRM bridge driver. We call it PRM.sys in Windows. And that bridge driver would use that information to invoke the PRM handler. Alternatively, you can do what's called direct call. And direct call, the operating system driver is aware of PRM. So it's not abstracted from the idea that a PRM handler is going to be called, as in the other case. In the ACPI case, the driver doesn't necessarily know whether an SMI or a PRM call is going to take place inside the ASL code. In direct call, the driver directly calls the PRM handler. It does that by using an ioctl made available by the bridge driver. And so it would give the GUID and this structure called the parameter buffer which has come up in both cases, right? So we'll cover that up ahead. It gives that to the bridge driver, and then the bridge driver uses the information provided to it through the ACPI table, and it invokes the PRM handler. And so as it shows below, those would be invoked in lieu of the SMI handlers. So now we'll cover the op region. So the op region was kind of central to a ASL code being able to call into a PRM handler. So at the top left, we have a generic op region definition. The platform RT mechanism is the type of the PRM op region. It has a single access type allowed, buffer access. As I mentioned, you need to build up that 26 byte buffer with things like the PRM handler GUID you want to call, and maybe some parameter information that you want to pass to it. And then you write that to the op region to actually trigger the PRM call. And so this is showing, the op region over here, and you would write your ASL data buffer that you build up to this field in order to actually trigger the ACPI bridge driver or the PRM bridge driver to invoke the PRM handler. So the ASL data buffer, as it's currently defined, is 26 bytes. It's used as the request response buffer for the handler. So you would put, your request information in the buffer, write it, it would get back the response information from the handler. It contains the PRM handler GUID, which is obviously critical to call the correct handler, and then it returns back a status from that handler that can be bubbled back up through ASL. Now we'll look at the PRM files and data structures. This is how PRM is organized in terms of the actual code and design. So PRM is a PE32 based image, very similar to EFI images. They are also PE32 images that comply or adhere to the PE COF specification. The PRM module itself has a DOS header followed by NT headers with data directories that have ultimately an export table. And we use the export table extensively for PRM. So this is typically used as as for dynamic linking inside Windows with DLLs. It's basically used to be able to convey information about the functions inside an image that a loader can discover to allow others to invoke those at runtime. And so we take that to our advantage in PRM so that we can have the PRM binary self-describe the handlers so that a firmware doesn't have to have baked knowledge about the handlers inside the PRM modules. You can add the modules, and then the firmware can dynamically discover what's available in that module and then pass that information to the OS through the ACPI table. We use the major image and minor image version fields in the optional header to communicate the image information about the PRM module itself. So if someone wants to know what version this PRM module is, it would use these fields. We did this because file system APIs allow this information to be easily read, and we can have a lot of pre-existing code get the image version information by doing this. Inside the export table itself, we have the PRM handlers. They have relative virtual addresses. That's what RVA is. That's the offset of that particular function from the base of the image as it's loaded into memory. And so in the firmware dispatcher, it will discover the PRM module. Because it's a PE32 image, a lot of the pre-existing code can actually be used to load this image in the memory and even rebase it. And then the RVA from the export table is used to actually figure out where the physical address of each function is. It discovers the functions through the export table itself. And the export table, as you can see, identifies the RVA with an ASCII name string. Now, in order to actually call this in the operating system, we're not calling it with ASCII name strings. We're calling it with GUIDs. So we need a way to associate a physical address with a GUID, because what's going to happen inside the operating system is it's going to give us a GUID to the bridge driver to call. The bridge driver needs to know what physical address that handler resides at to invoke it. And so we have this structure called the PRM module export descriptor that actually maps a GUID to a name. And so the firmware uses this structure to be able to map the ASCII name string in the name pointer table of the eData section inside the PRM module binary to a particular RVA, and then it can compute the physical address for that function using the RVA, and then it can put the physical address for that function into the ACPI table alongside the GUID. And so that way, the operating system has the GUID and the physical address of the handler. Now, PRM handler itself is very similar to UEFI runtime services code. It uses the same ABI as UEFI runtime services, and that was intentional to try to make this seamless as possible for operating systems to be able to invoke, since they already have to deal with UEFI runtime services today in many cases. And so the PRM handler has a PRM export API modifier on it that is used to have the linker put the PRM handler function into the export table of the module during build. And it uses the EFI API modifier there to use the EFI ABI. And it also has a parameter buffer and a context buffer parameters on it. We'll discuss those in the upcoming slide, but the parameter buffer is essentially a way for the caller to pass real-time kind of information to the handler. So it can like read a register or talk to another driver, get some data, and then pass it through the parameter buffer to the handler. The context buffer is kind of a generic resource buffer that the handler can use in order to have certain resources that it can basically make use of as it's executing. So the parameter buffer is allocated by the OS driver that calls the handler. And so the operating system driver might allocate a parameter buffer, fill it with some data, and then give the virtual pointer to that buffer to the handler through the function parameter. So it's based on a contract between the caller and the handler. So the actual data that goes into this is a contract between that OS driver and that handler. So the handler is essentially defining what it expects in its documentation to be in that buffer, and then the OS driver or the caller is providing that. Its purpose is mostly to provide that runtime data to a handler. You don't have to do this. You can provide null, for example, and it will, you don't have to pass any parameters if you don't need to. The context buffer is allocated by the operating system kernel itself. And so this is much earlier in the boot flow. Whenever the operating system is kind of getting that ACPI table, it will typically construct this context buffer because it has all the information it needs to be able to do that. So it will generally do that as part of its cache list. And so this information is based on the information provided by the PRM ACPI table. So the buffer itself is built based on a lot of the data that's provided in that ACPI table. And its purpose is to provide a table of pointers to various resources that the handler can use. Some of those below are like the static data buffer and a list of MMIO ranges. And so the static data buffer is a buffer that's actually allocated by the firmware to pass firmware information to a handler. So today with SMM, because the SMM is actually launched inside the firmware boot environment, the firmware is able to pass a lot of information to the SMI code, SMI handlers or SMM code. It's able to do that fairly easily, conveniently. And so this is a mechanism where the firmware can allocate this buffer. It can put the pointer to that buffer in the PRMT ACPI table, and then the operating system will get that physical pointer to the buffer from the ACPI table, convert it to a virtual pointer, and then put that virtual pointer inside this context buffer. And so the general theme is that all the pointers in the ACPI table are physical, that are provided by the firmware, and then the pointers that are produced in the context buffer from the ACPI table are virtual. And so the runtime MMIO ranges is an array of descriptors for MMIO ranges that might need to be accessed by a given module. And it contains the physical to virtual mappings. So if a module might need one of its handlers to access an MMIO range, in the firmware boot time, it would declare that MMIO range inside this array of MMIO range descriptors. And then those ranges would be converted to the virtual address map so they can be accessed inside the operating system. And as far as the firmware init flow, this is kind of more of an implementation detail, but if a module requires any resources to be accessed, such as the static data buffer or MMIO, it does that by providing what's called a PRM config protocol in UEFI or EDK2. And so It doesn't actually need to write a lot of code to do this generic work, like building this MMIO range descriptor list. A lot of that's done by you describing the resources you need with this protocol, and then the protocol goes into a generic config driver that will produce those mappings. Some of the key data structures are, we have a PRM module export descriptor structure. So this contains information about the PRM module itself as exposed by the export table. So it has like the GUID of the module, the platform GUID. And so the platform GUID uniquely identifies a platform being targeted by PRM. So you might have a PRM module that has the same module GUID for two different platforms, but the platform knows which PRM module should be applied on that platform by the platform GUID. It has a handler export descriptor structure. So this is an array of those handler GUID to name mappings. So each PRM module export descriptor structure will have this array of these GUIDs and names that associate with each other, so that the firmware can use that to build up the ACPI table. The top level PRM ACPI table has a bunch of industry standard fields, but at the end, it has a module info structure array that describes each PRM module. The module info structure, which is an entry in that array, contains the identifier, which is the GUID of the PRM module itself, followed by information about the handler, such as the handler count, and finally the runtime MMIO ranges that might be accessed by that module. And then at the end, it has the handler information structure array, where each entry of that array is a handler information structure that describes the physical address for that handler, the static data buffer that may or may not be used, and the ACPI parameter buffer that may or may not be used. So the firmware would fill in the physical address based on those PRL module export descriptor table, using, as I mentioned before, mapping the RVA back to the physical address. And if the PRM module wants to use a static data buffer, the pointer to that buffer would be put here. Otherwise, it can be 0, for example, if it doesn't need one. This is showing how it all looks on a real system. So if that was a little confusing, this is what it actually looks like laid out in memory. You have the top level table kind of in gold here, followed by the module information structure. And then after this module information structure, you have 3 handlers in different shades of blue. And then you have a second module followed by 1 handler. And then finally a third module that also has 3 handlers. And this is just kind of showing what that looks like actually being read back from the operating system. Over on the right, we have a module export descriptor structure that has 3 handlers. And actually, this is the export section itself that has a module export descriptor structure. As you can see, that's at RVA 4020, and then it has 3 handlers up in the code section there. So this is just showing what it looks like when read back from a real system. This is based on slightly older data structures, so it's not completely up to date with what's in the open source repository, but it's just meant to give you an idea. So as far as the open source firmware goes, we have a branch on EDK2 staging called Platform Runtime Mechanism. This has the generic infrastructure implemented for UEFI and EDK2. It's currently used with no modification to support PRM on IoT, client, and server systems. What that means is that we take this code and we use it as the generic infrastructure to be able to load and execute PRM modules on all these different types of systems, and we don't change this code. The idea is that you really should just be able to write your PRM modules, and those should be able to load on this generic infrastructure without you really having to do much lifting yourself to actually get PRM up and going on the system. We really want you to be able to focus on writing PRM modules, not necessarily having to focus on having to do a bunch of this, spec-defined buffer handling and all that kind of stuff. Building the ACPI table, all of that is intended to be done automatically with the open source code. Up there, we have 4 sample modules available. So these demonstrate how you can actually write a PRM module, and you can also use them to play around with PRM on a given system. So if you want to actually try taking that open source code, moving it onto a system, loading some PRM modules and seeing what happens, you can do that with those sample modules there. We use those for testing, validation, and demonstration purposes in many different cases. So those are available for you to use. Over on the right, we have a shell application for the UEFI shell that provides information about the PRM modules on a system, and it can be used to actually execute modules as well. So if you don't have a PRM aware operating system yet, you can take this shell application and you can actually make sure that your PRM modules are getting loaded by the infrastructure correctly, and you can execute your PRM handlers in this application. So this, I'm just going to play some example of it, discovering what PRM is available, what PRM modules are available on this system, and actually calling those handlers and getting the results back. This was done on QEMU, the open source emulator over on the right. So we have documentation that covers the PRM, how to write modules, how to integrate firmware. That's available in the open source repository. We also have a closed source specification that we are moving to become public. So that's planned for adoption by the UEFI forum, and that should be made available soon. More details will be provided about that on the repository as it becomes available. Finally, this has been ported to many different platforms. It's been ported to QEMU, using the OVMF package. There's a link here to an OVMF fork that does that. It's been ported to the open source project Mu Q35 QEMU package as well. It's been ported to Hyper-V, for example, and many other virtual machines for testing. These are the two main publicly available open source places you can go to test PRM and get working examples up and going. And so the current status is on the firmware side, we have the generic code up on EDK2 staging. So that's where we put code that is being staged for the EDK2 project. As I mentioned, the specification here is planned for adoption by the UEFI forum. We have 4 sample modules added there, and that UEFI application to help people get started quickly and easily if they don't have a PRM aware OS. And a lot of this focuses on UEFI and Tiano Core, but really the idea is that any firmware can do this. None of this is meant to be specific to UEFI and Tiano Core. I just wanted to mention that. We just have started with that because many of the systems that we're working on use that type of bootloader, but you can incorporate this into other types as well. So the specifications, we have some ECRs outstanding for the platform RT mechanism op region type with the ACPI working group. We have the specification that's currently closed source being moved for adoption to the UEFI forum. That work is in progress. On the tool side, IASL has actually supported this op region type since 2020 05-28 version. The Microsoft ASL compiler supports it in all Windows Insider SDK builds. Our Linux support is still being formed. We have some code patches being created, and those will be made available for community review. And so we have some support pending there, but no firm timeline. On Windows 10, we have implemented support in current Windows Insider builds, and this will be available in all future versions of client and server Windows. In terms of real-world SMM to PRM conversion, Microsoft is evaluating usage of PRM in Azure as it becomes available and enabled in future platforms. It's particularly an attractive point of PRM is its ability to be, number one, moved outside SMM to help with some of those system use cases that I highlighted and some of the impact you can have, but also to be able to update the code without a system reset. And so we see a lot of potential there. The conversion of relevant SMM handlers on client systems is in progress. So this is something we're working through on what are some real world SMM handlers, outside the examples that are shown here and some of the more server focused use cases that we can do on client as well. And so we're looking at that. And that's all for the presentation. Please check out the branch to learn more. That will have information about the spec as it becomes available. You can also submit patches for that branch if you'd like to using the EDK mailing list. Thank you very much.